All right, so talking about chapter 2. So let's start with 2.1. We learned a couple ways that we can describe matter, give properties to matter. And so those main terms are going to be intensive and extensive. So if I have a random piece of metal and I want to figure out what type of metal it is, should I use intensive or extensive properties? Intensive. These literally have to do with identifying. So I want you to think of identifying. So I'm going to again emphasize the fact that they both start with I. So hopefully this helps you. Intensive are identifying properties. So examples, what are some examples we got? Density, mass is the next one. We got density as an example. What else? Say color, color, hardness. Now I want to also bring up boiling points and melting point. Those are super important for identifying. So I'm going to abbreviate those. Boiling point, melting point. So we could go on and on and on and on. We're not going to exhaust the list of intensive properties. Extensive depends on what? Amount. Exactly. Extensive depends on our amount of sample. So, Isaiah, what's an example for that? Mass. What else? Volume. Any other ideas? Blank, did I hear that? Awesome. Okay. So again, I'm not going to sit here and write out a million things, but it sounds like you guys are getting the idea. So any questions on figuring out what the difference is between intensive and extensive? Cool. Okay. I'm also not going to sit here and go too crazy on states of matter. We've talked about this a lot. But if I ask which one's a solid, is it left, middle, or right? How do you know that? It is uniform. In what way? Right? So it's ordered. We refer to our solid as our most ordered when we're thinking about the atoms that make it up. Liquid, they start to have a little bit more freedom. They get a little disordered. Gases just go crazy. All right. So solid, liquid, gas. Now, thinking about the changes between solid and liquid, liquid and gas, we refer to those as our phase changes. When we are talking about physical properties, we said, hey, some are reversible, some aren't. If you freeze an ice cube, so you take liquid water and freeze it, can you undo that? You can't melt it? You can, right? So phase changes are reversible. Now, what about if we talk about irreversible physical changes? Does anyone remember what my example was? Tearing paper. So this would be tearing, cutting, smashing, where all the pieces still have the same physical properties. You just changed how it looks a little bit. All right. Any questions on 2.1 material as of right now? Feeling good? All right. Yeah, go ahead.
Anything on this review that won't be on the is there anything that's not on here?
Oh, yeah, this isn't necessarily the only thing you should be studying, right? I like to highlight some of the main things, but always you have a study guide, and I always recommend going back through notes too. All right. Now, 2.2. We talked about mixtures in 2.2. as for our mixtures, in order to be considered one, you need 2 or more, we're gonna call them phases. How are they combined? Physically or chemically if it's a mixture? Physically. That is super important. This means if they're physically combined, we can separate them using physical methods as well. And so we had 2 main classes that we split our mixtures into, heterogeneous and homogeneous. And I think food is the best way to think about these differences. So just generally, heterogeneous, we're gonna say, yeah, you can see the different phases. So what are some examples? It doesn't have to be food, but where we can see the different phases. Salsa, I talked about that one. I had a really good idea for one this morning. What about trail mix? You can really see the different peanuts and M&Ms. Cereal's fantastic. Shout out to Lucky Charms. That's my favorite. So we can see the different parts that make it up. Now, homogeneous, we also call them solutions. Typically, these are things that we think about are liquids. Now you cannot see the separate parts, the separate phases, or different. So I think it's easy to think about drinks for this. So, for example, my favorite, coffee would be a good example, right? What else do you think? What just looks like just one liquid, but actually is made up of different things? Hot chocolate's great answer. Fruit punch works. Yeah, because technically caffeine is one substance, right? Even if you put caffeine powder in water, that technically is a mixture because you can physically separate them back out.
So would it be?
That would be homogeneous, right? Because you can't see the caffeine in it, right? So then that would make it homogeneous. All right. What? Smoothie? Now, if you can see the seeds in it, I might argue with you.
Mashed potatoes.
With like butter in them? Okay, fair. If you can't see the butter, I would say if they're really creamy. Gosh, now I want mashed potatoes.
I just want food at this
I know, right? We're all starving here. Okay. Any questions on mixtures? Like, sounds like you guys have a pretty good idea. All right, let's talk about substances. Now, when I say substance, so for example, apples and oranges are fruits, right? Fruits is kind of our big umbrella term, apples, oranges, bananas, etc. When I say substances, it's like fruit. You can have elements and compounds in it. So substance is just kind of a more general term. I'm going to color these for you guys just so it's easier to see kind of what's going on here. I apologize, black and white is not always the easiest for these sorts of things. So talking just about elements, we like to consider these to be our simplest form of matter, and we cannot break them down. So we'll just say cannot break down. Versus our compounds, these can be broken down into the elemental parts. So can be broken into elements. Now, why is this considered an element and not a compound? What? Exactly. They're two of the same exact thing. To be a compound, it has to have two different elements that are chemically combined. So yes, these are chemically bonded, but it's the same exact thing. So that's still considered an element. Versus Now, when you start mixing oxygens with hydrogens, that gives us a compound. Now, compounds are two or more things together, but so are mixtures. What's the difference? What's the difference between compounds and mixtures? Compounds do have a formula. Very good point. Yeah. Yes. So what is that? So what I'm trying to get at here is how are they combined? How are the two things combined in a compound versus two things in a mixture? Exactly. So in order to be a compound, they have to be chemically combined versus mixtures are physically. So yes, they are both contain two or more different things, but it's all about how they come together. Okay. Now, what I mean by this is I'm going to kind of make up my own little particle diagram here for you. So if I give you this particle diagram, is this a pure substance or a mixture?
Mixture.
Correct. It is a mixture of this and this. Now, in the individual boxes, are those mixtures or compounds? They're compounds. So this is a compound, where when you look at the bigger picture is a mixture, okay? So you don't necessarily have to copy that down. If you want to do something like that, that's fine, but I just want to explain that slight difference. Any question on elements versus compounds versus mixtures? Okay, what? Yeah, yep. Like salt water is two compounds, NaCl and H2O. Yeah. Exactly. What I might do is give you one of these and say, circle what is true. And I'll say mixture, pure substance. And you just have to circle which one it is. Right. So that's like if you go on your review guide with all the different particles. I'm just trying to get you used to identifying, is it an element? Does it have a compound? Is it a mixture? Is it pure? So good question. Any other questions? All right, let's talk about chemical changes here. So in chemical changes, we have some sort of reactant or reactants that go to form products. What has to be true for it to be a chemical change? There's always a change in what from reactants to products. What's that fun word? That composition. Exactly. So when you go from reactants to products, there is always a change in composition, identity, properties, however you want to think about it in a chemical change. Now, we have actually done a whole lab learning about 4 clues for a chemical change to occur. What did we look for in our last lab with all our test tubes? What's one thing? Color what? Color change, yes. What's another thing we looked for that would indicate temperature change? We're looking for 2 more here. Yeah, precipitate. Exactly. Precipitate formation. So forming a solid there, and then gas formation as well. Now, we list color change as one of our clues for a chemical change. But if I say sulfur is yellow, is that a chemical or physical property? It's a physical property. So just looking at a piece of sulfur and saying it's yellow, did I have to change sulfur into something else to realize that? No, so that makes it physical. But if that sulfur starts turning brown, that's an indication of a chemical change because there's a change in color. So words like change really can make a difference when talking about chemical and physical properties. All right. Any questions on the 4 clues? All right. Now I'm going to make sure you guys are ready to do some algebra. You will have 1 algebra question on your test, but you guys got this. All right. So it has to do with the law of conservation of mass. Why do you think it has to do with this? The mass of what has to be equal to mass of what? Yeah, what we're reacting better equal what we're getting in terms of mass. So this is like when we talked about bonfires. When you light wood on fire, does the amount of ash seem to be about the same as what you started with? You think so? I was like, what? Not really. So we have to think about where did that go? It's not like we just, the matter of wood is gone. So that's the smoke, the gas, the other particles that are being put into the air is actually where a lot of that mass is getting lost. So again, reminding ourselves that mass of products better equal the mass of the reactants. Or thinking about it in a sense that matter cannot be created or destroyed. So what I'm going to give you is a generic reaction. I'm going to say I have some random reactant, 1 plus another reactant that forms a product, P1, and another product here. So this is just going to be like our reactants go to our products. And I'm going to tell you, I know that I have 6 grams being added to 8 grams of reactant 2. The only thing I could figure out, let's say for the product side, is I have 10 grams of product 1 that formed, and I want to know how much product 2 I should have then. So all this is just an algebra equation. So I'll show you how to do it. Anywhere you see a plus, once you identify what masses go with what one, you put a plus between your amount of grams. So I'm going to do that on both sides here. And then anytime you see the reaction arrow, that's like an equal sign, right? Because our reactants better be equal to our products. So we end up having 14 grams is equal to 10 grams plus some unknown. So how much product 2 should we have? 4 grams, exactly. So I'm going to continue, subtract 10 grams from both sides. We get 4 grams as our unknown for product 2. Any questions about this? You guys think you can handle this algebra? Love it. All right, so notice I used my units. I'm gonna make you guys show your work for this. You need to make sure you're using your units. Now, do you have to go as far as I did for this? No, it's fine if you skip this step, but make sure you're showing your work with units, please. All right. Any questions before jump over to the back side? Okay, so what I want you to do is I want you to start thinking, figuring out if you can fill in this table with the different states of matter. Remembering that when I say definite shape, all definite means is cannot change. All right. And then I'm also going to give you one more practice algebra question, just like the one we just did, for you to try. So underneath there is an additional algebra thing for you guys to try. All right, so let's go through this table here and talk about what we got. So a gas, does the gas have an ability to change its shape? then it cannot have definite shape. So we say no. That's the first thing we fill in is no. What about its volume? Can it take the volume of its container? Then that also gets a no. I'm gonna go through, we'll come back to compressed here in a second. What's the next state then that belongs to the line below? Liquid. We know that its shape is not definite. If I take this hand sanitizer, I can move it around. It'll take the shape no matter how I tip it, right? But if I stir it long enough, do you think it'll start to fill up? No. So it does, however, have definite volume. And lastly, we have solid. We know that for example, this outside container has a specific shape. Its volume is not going to change, so that is definite as well. And so let's talk about compressibility. So if I have, for example, my little cube here, if I try to push this down and I try to push the air down that's below my hand, what's easier? Air. Air's super easily compressed. Solids are not, however. So yes and no, that would be the filled in table. Any questions about that? Okay. What do we get for our answer for the bottom problem? Yeah, love to hear. So you should have got 35. I'll walk through it real quick. So CH4 21 grams. I will place that underneath it. CO2 is 15. That goes here. H2O 41 goes here. Everywhere I see a plus, I put a plus. Everywhere I see the reaction arrow, I put an equal sign. And so that means our unknown is O2. We want to know. And the question will say, how much oxygen did we use? So solving for that, you get that 15 plus 41 is 56 grams. So that's what your products equal. And we have 21 grams plus our unknown. Subtract 21 grams from both sides. That gives us that our unknown amount of grams, it's question mark down to number 2, is equal to 35. So that's your oxygen. Any questions there? All righty. So you guys